So our last topic in chapter 33, and as you remember when I started chapter 33, I said this is a really huge chapter. There's a lot of topics in here. So the last topic is polarization by reflection. What happens is you get light coming in. Okay. It's going to refract. So you get some theta 1, get some theta 2. Well, an interesting thing happens, and that is that as theta 1 gets bigger, theta 2 gets bigger, until eventually, if theta 1 is really big right here, okay, then what happens is that theta 2 here is going to be like that. It's not going to get as big as fast, assuming that N1 is greater than N2. So this is N1, that's N2. But what's going to happen is that the light coming here is all different polarizations. Some polarization is perpendicular to the, and some is parallel to the surface. When it's really shallow like this, the light that's perpendicular to the surface, it turns out that it's going to go ahead and refract, but light that's parallel is going to cause the electrons to move back and forth parallel to the surface, and that's actually going to be, interestingly enough, cause a reflection right there. And so you'll get a reflective piece. And so that reflection is all going to be polarized parallel to the surface. Well, in fact, one thing we often discover is that frequently when light hits a surface, even though we get refraction, you get some reflection anyway. And so what we find is that at the critical case, okay, so the critical case in which you get refraction and reflection, that if this is polarized parallel to the surface, and this is polarized, there's some be parallel to the surface, but a lot of it's going to be perpendicular to the surface, that the two polarizations are perpendicular to each other. So this magic angle, if in other words, if this angle is greater than this magic angle where this condition is met, then from that point on, for all greater angles, you're going to get reflection that's polarized. Okay. Now, like I said, you always get a little bit of reflection, but the reflection that comes off is going to be polarized. And we call this the Brewster angle. Okay. Okay. Well, we know that this angle has to equal that angle. So this is our reflected angle right here. Okay. And so what we look at here is we notice that on this side over here, the Brewster angle plus 90 degrees plus the reflected angle has to equal 180 degrees. So that means the Brewster angle has to, plus the reflected angle has to equal 90 degrees. Okay. So that means the reflected angle has to equal 90 degrees minus the Brewster angle. Well, we also know that Snell's law holds. N1, again, this is N1 and N2. N1 sine the Brewster angle has to equal N2 sine of the refracted angle. Okay, so N1 sine Brewster angle equals N2 sine of 90 degrees minus the Brewster angle. Well, you know you've learned trig identities. Okay, and you remember trig identities, you know, at one point you had a trig teacher saying, hey, you're going to need to know the trig identities, you ought to learn them. Aha, today's one of those days. Sine 90 degrees minus an angle is cosine of that angle. Okay, so that means that N1, sine over cosine, So tangent of the Brewster angle is going to equal N2 over N1. In other words, the Brewster angle, this magic angle at which you get this, is going to be inverse tangent of N2 over N1. So anytime light hits a surface, and if that angle is greater than or equal to the Brewster angle, you will get light that is polarized, parallel to the surface. Okay. So that's an interesting sort of thing. Turns out that this happens quite a bit. So it can happen, for example, if you have water. So imagine that you've got air up here. So this is air. This is water, so 1.33. So if the sun is shining and the sun is shining above, you've got the Brewster angle here, you get reflected light parallel to the surface of the water. Well, the Brewster angle for water will be the inverse tangent, you've got air above it, will be inverse tangent of 1.33 over 1. So that is going to be equal to 53.1 degrees. So anytime the sun is shining, it hits water, and the angle relative to the horizontal is, well, this theta h. Theta h is going to be 90 degrees minus the 53.1. So that means it's going to be equal to 36.9 degrees. So anytime the sun is hitting the water at an angle that's less than 36.9 degrees, you get horizontal polarization. Now, it turns out that's an interesting thing because this happens relative to other things too. I mean, I could have glass. If I had light reflecting off of glass, okay, then it's going to be a similar sort of thing. So if it were glass, so if I have glass, so N equals 1.52, this is air. So again, we get a Brewster angle. The Brewster angle is going to be the inverse tangent of 1.52 over 1. So that turns out to be 56.7 degrees. So that means if that means this angle there was 33.3 degrees. So anytime light hits glass at an angle that is less than 33.3 degrees from the parallel to the surface, you're going to get a reflection that is polarized. Now, that's interesting because all the light reflects off this way. So if you had a polarizer that blocked that orientation, then you would be able to notice that you would kill the glare of the reflection. Well, again, even a road. The road has an index of fraction, and so the light coming in would come off polarized like that. So if that's glass, if this is like a wet road here, it's water reflecting off of there, and so here you are, and you don't want to see that glare of the sun reflecting off the road. So what you do is you wear sunglasses that have vertical polarizers in them, and that blocks the horizontal polarization. Well, there's a company called Polaroid that started marketing sunglasses that do that. And so if you're wearing polarized sunglasses and it blocks that glare, if you turn your head sideways, you see the glare again. And so this is an example of polarization in action. And so when the sun's low and you get this sort of glare off of things, your Polaroid sunglasses will block the glare. Likewise, a glare off of glass, it would block the glare off the glass as well. And now another interesting thing is that you have to have Polaroid sunglasses to block the glare, but there are a bunch of insects out here that are flying around, and they actually have horizontal polarized lenses in their eyes. Now, why would bugs have horizontal polarized lenses in their eye? That is so they can more easily see the horizontal polarization. So late in the day or early in the morning, the bugs would see horizontal polarization and fly towards it, because that in nature, about the only place you get a smooth flat surface is water. And so they're looking for water. Now, that actually unfortunately has another problem, and that is that today you get an automobile with headlights. The headlights reflect off the road surface, horizontal polarized, and that actually causes the bugs to fly down the road, because now they're heading towards this, what they think is water, and it's really a car's headlights reflecting off the road. And so that's one reason that you get so many bugs splatted onto your car right just after right near sunrise and sunset. Is that's when the bugs are out looking for horizontal polarized light, and they're mistaking the headlights of your car reflecting off the road as water. So anyway, this is polarization by reflection.